14 identical resistors, each of resistance R, are connected as shown. The equivalent resistance between points A and B is. So, between point A and B, we have to find equivalent resistance. So, we can connect a battery between these 2 points to get an idea of the current distribution. As we can see, the circuit is symmetric. Just forget about these 2 resistances first, CF and DE. Then you can see the circuit is symmetric below and above the line AB. Just forget these 2 resistances. Okay. And then these 2 resistances are connected diagonally in the identical manner. So these 2 resistances doesn't destroy the symmetry of this circuit. Let us suppose I be the current from the main branch. Then we can see at the point A, lower and upper half will receive the same current I by 2, I by 2. Then what happens? Let's see. This is resistance R. This is another resistance R. So drop in the voltage when we move in the direction of current across the resistance, then drop in the voltage will be IR. So in this case IR by 2, we reach the point C, and here across AD also the same drop of the potential is there. So starting from a common point, there is a same drop of the voltage IR by 2 in this branch and IR by 2 in this branch. That means the potential of the point C and the point D must be same, because we are reaching point C from the point A after minus IR by 2 drop of the voltage, and in the same manner in the branch AD also. So C and D both are at the same potential. That means there won't be any current flowing between C and point D. So C and D can be placed at the same location also. Whenever you encounter such points whose potentials are same, then you can redraw the whole diagram assuming those points at the same location. And here in this case, with the same logic, we can see that E and F are equipotential points, means there won't be any current between E and F, so this resistance will also go waste like the resistance connected between CD, because there won't be any current between these 2 points. So E and F will be drawn at the same location. So now if we redraw this circuit, how? Let me show you. First thing, let's make points. So here it is a point A, and here somewhere is another point B. Okay, so we have to find equivalent resistance between A and B. We have seen that point C and point D both are identical in potential, so we have to put these 2 points at the same location. Okay, because these 2 points are at same potential, so they can be put at the same location, and whatever connected between these 2 points will go waste. And in the same manner, E and F also will be there at the same location. So this point will be treated as E as well as F. And there is another point which is G, and there is another point which is H here. Now we can use one by one all the resistances in this network. So let's start with the point A. So between A and C there is one connected, between A and D there is another connected. So we are counting these 2. So these 2 resistances, so one is R, another is R. Okay, between A and C, between A and D, because here C and D are same. This particular resistance has gone already. And in the same manner, we can use EB and FB. EB and FB. So we have considered this, we have considered this. Now, here you can see that C and F, this resistance is connected between C and F. C point is here, F point is here. So C and F, this particular resistance is connected. So we have considered this. D and E, this particular resistance is connected between D and E. D is here and point E is here. So we have considered this now. Between C and E, this resistance is connected. C and E. So C and E, this resistance is connected. Similarly, D and F, this particular resistance is connected. So D point is here and another F point is here. And in the same manner, between D and F via H, two resistances are connected, these two, so we have considered these two, and similarly these two resistances are also there, so these two are also considered. Now we can see that this R and this particular R, these two are connected in series, and similarly these two R's are connected in series. So we can replace these two with 2R, and similarly these two can be replaced with single resistance 2R, and this 2R and 2R connected in parallel, so equivalent of these two becomes R. That means we can replace these four resistances by R, and then including that R, there are these four R's also which are all connected in parallel. So what we get here is the point A, and then here R by 2 is their resultant, and then there is a R by 5 because here we have 5 R's connected in parallel, and similarly here two resistances are connected in parallel, so R by 2. So here is the point B. So these three resistances are connected in series. So equivalent resistance between points AB will be equal to how much? R by 2 plus R by 5 plus R by 2. That means it is equal to R by 2 is R, so it becomes 6 R by 5, which means 1.2 R. So option D has to be the correct option to this question.